you know, to hear something that you may have missed, or if for future reference, if you miss a class, you can always catch up by watching the YouTube video. I'm just going to record, you know, the lecture on YouTube. Okay, let's see here. Let's see. Okay, so we are now live on YouTube. Okay. Oh, you know, I need to mute this. Okay. So let me go to here. All right, so good morning, everyone. Firstly, let me apologize for my absence last week. I just had the days confused, and you know, this is as a result of me recovering from the previous semester. My brain was so fried that I had the days confused. So that's the reason why I was not present to conduct the class last Wednesday. So let me first introduce myself. My name is Pete Nicely, and I'll be the one who will be guiding you through this course, which of course is General Chemistry 1 lecture. And basically the plan for today is that firstly, we're going to go through the syllabus. The syllabus is posted in Canvas. I don't know if you have downloaded it before, but if you haven't, you may want to do so now that you can follow along. So basically, this is, oh, let me, I forgot to share my screen. That's another thing I tend to forget to do. So let me share my screen. Okay, can you see my screen?
Yes.
Okay, good. All right. So this here is, of course, the Canvas shell for this course. So most of everything that we will be using in this course will be located in the file section. So I'm going there right now so that I can pull up the syllabus. So, oh, apparently I put the syllabus here. The syllabus is normally saved in this syllabus folder right here. I made some changes to it. So if you downloaded it from before, you may want to go to the folder which is labeled syllabus and download the most recent version of the syllabus. So let me do that now. Okay, so let me make this full screen. All right, so what I'm going to do is go through the syllabus first so that we're all on the same page as to what you should expect from this course. And then I'm just going to go directly into the course itself, starting with chapter 1. So as you can see on the very first page of the syllabus, there's some general information, course information, the title, the course number, number of credit hours, instructor name, and of course, this course would be located online, and we'll be meeting every Monday and Wednesday from 9 a.m. to 12:40 p.m. Of course, that's a long time to be sitting in front of a computer screen and listening to me go on and on about chemistry. What I'm going to try to do for this summer period is break up the instruction into 50 minutes portions. So basically the first 50 minutes will be from 9 to 9:50. The second 50 minutes will be from 10 to 10:50 and so on, all right? Hopefully that will provide some break from the monotony of this course. As far as where I'm located, physically speaking, I have 2 office locations depending on whether or not you're referring to the Citrus campus or the Ocala campus. So at the Citrus campus, I would be located in building 3, room 208, and that should be 208E. I'm going to make that change and re-upload this syllabus. At the Ocala campus, I'll be located in building 2, room 220I, all right? Now, I must say that apart from Monday and Wednesdays, which I'll be, you can find me on the Ocala campus, I pretty much will be off campus for the rest of the week during the summer period, all right? Just to let you know. My office hours would be on Tuesdays, every Tuesdays from 2 to 5 p.m. And my telephone extension, again, it depends on the campus. At the Ocala campus, it would be extension 1459. Actually, it should be 1450. I need to make that change as well. At the Citrus campus is extension 6202, and my email address is given nicelyp@cf.edu. And below that table, you see a statement concerning emergency closure. So if something happens and class has to be canceled because of some unforeseen happening like natural disasters, etc., then you can call the number provided. Actually, there are two numbers provided. One is a toll-free number, and you can also check the college website because they normally will provide information there concerning those issues. Also, it is mandatory that each student obtain a Skype account. And there's a link that is provided for you to basically set up an account if you don't already have one. As soon as you get that account set up, make sure that you send me a Skype contact request. And when you do so, make sure that you give your name and the course number. And that's important because, from time to time, I would get solicitation messages via Skype. And I want to make sure that I'm able to distinguish between those messages and my students. My Skype address is provided. It's pete.nicely. And to sweeten things a bit, there'll be a 10% bonus point added to the first test only for obtaining the Skype account, all right? Now, the reason why I demand that my students obtain a Skype account is because it facilitates meetings and consultations, especially during office hours, all right? And one of the good things about Skype is that I can share my screen, and while we're talking, let's say, for example, I'm explaining, some concept like balancing equations, whatever, then I can explain to you while writing on my screen, and you can see it. And therefore, you can better able to understand what I'm trying to communicate. So that's the reason why I insist that my students obtain a Skype account. As far as contacting me via email, the best way to do so is through the Canvas system, all right? Now, I gave you my email address earlier, but I would recommend, and I would very much prefer, that you contact me by email through Canvas. And the reason why is because for some reason, well, in the case of the college email, if you send me an email from some external source or even from your own college email address, what will happen is that that email will be shunted to the, what do you call the folder? The junk folder, basically. And I very rarely check that folder. So it's very important that if you contact me via email, you do so through Canvas. Another advantage of using the Canvas system for email communications is that when you send me an email, I can immediately see what course of mine you're enrolled in. And therefore, I can, based on that information, promptly answer your questions or queries or whatever discussion you want to have, all right? So as stated here, I cannot guarantee prompt response to an email sent through the regular college email. If you want a prompt response, it's best that you do so through the Canvas system, all right? Okay, course description. The prerequisite for this course is, of course, introductory chemistry or equivalent, which would be high school chemistry, with MAC 1105 with a grade of C or better. Course description, this will include an expanded review of the introductory chemistry course, and will cover topics such as atomic structure, bonding formulas, nomenclature, reactions, stoichiometry, gas, solids, and liquid states, all right? Objectives, this is the first semester of the general chemistry sequence offered at all state colleges and universities. So this course is basically the same as any other course of this type at any of the public colleges and universities in the state, all right? So this course, General Chemistry 1, is the same as General Chemistry 1 at University of Florida or University of South Florida, whatever, all right? And in this course, the students should develop an understanding of atomic and molecular structure, the periodic table, gaseous solutions, chemical reactions, and stoichiometry. It is expected that the students will have a background equivalent to, of course, the introductory chemistry. The textbook for this course is one that is totally free and available in Canvas. It's called OpenStax Chemistry. And let me show you where in Canvas it's located. Hold on 1 minute. Let me go here. Let me close this out. So you look for the folder which says OpenStax text. Click on that. And if you click on that, basically that will download the text. And it's a relatively large document, as you can see here, 325.5 megabytes. So it will take some time to download. All right. I understand, of course, that there are copies of this very same textbook available in the bookstore. And if you want to buy that, that's fine by me. I think it's relatively cheap. If I remember correctly, the last time I heard it was about 50 bucks. All right. So you have that option as well, even though I can't understand why you'd want to go with that option and not take the free option provided. Okay, let me see here. Where is the syllabus? Okay, so here's the syllabus again. In addition to the textbook, you need to get a simple non-programmable scientific calculator with certain capabilities such as the square root, logarithm, and exponential functions, all right? And of course, your calculator will be used when you're doing your tests, quizzes, exams, and so on. Well, there'll be no quizzes, I should say, so I should just limit it to tests and your final exam and your assignments. And of course, you're expected to bring your calculator so that we can work together on calculations in class. How your grade will be assessed, you'll be given 3 exams, each worth 100 points, and they'll be given at the dates below. And these will be take-home exercises. The lowest grade will be dropped, and there will be assignments given during the course, and no assignments, this should be assignments, not quiz, no assignment score will be dropped. And everything must be done in ink, no pencils. And everything must be done, of course, well, handwritten. I should have included that as well. So I won't be accepting any typed work. And basically how your assignments and tests will be submitted is basically what you're going to do is scan your written completed assignments or tests, all right? So you can scan them and then save it as a PDF document. Very important. I'm going to stress that over and over again. Save it as a PDF document, and then you can upload it into Canvas, all right? If you don't have a scanner, no problem. Your cell phone, you can take pictures of your assignments using your cell phone, but again, that assignment, even though it's on a cell phone, must be saved as a PDF document. And I think there's some YouTube videos that shows you how to do that, all right? Okay, so the next thing we're going to talk about is the test dates, and these are the dates that are given here. And the final exam date, we'll announce it shortly.
If I may.
Yes, sir.
It looks like you have 5/16 for the last test date.
Oh, yeah, that should be, I think that should be 6/16, if I'm not mistaken. Yeah, thank you for pointing that out. That's another correction. You know what? Let me make a note of these corrections I need to make. The first one was the Ocala extension number. And the next one.
You have
this,
the
I think,
Citrus building and room number for your office.
Oh, yeah, that should be E.
I think.
Yeah, that should be E. Yeah, thank you. And I think this should be 6/16. I'm going to check and make sure, but I'm quite sure that's what the date should be. All right. I think that's it as far as corrections so far. Okay. So let's move on to a further discussion of how your grade will be assessed. So as you can see here, this shows you the breakdown as to how each type of assessment contributes to your final total grade. So your exams, which means basically the regular semester test, will be worth 50% of your total grade. Your assignments will be worth 20%, and the final exam will be worth 30%. So just to give you an idea as to how your grade will be calculated, let's say, and this is a hypothetical situation where a student gets an average of 85% for the exams, 82% for the assignments, and 90% for the final exam. So basically, because the exams are worth 50%, I'll multiply the 85 by 50, and that gives you 42.5 out of a maximum of 50 percentage points. As far as your assignments, that should be assignments, not quizzes. That is worth 20%, so I'll multiply the 82% by 0.2, and that gives you 16.4 out of 20. And the final exam, which is worth 30%, so I'll multiply the 90 by 0.3, and that gives you 27.0 out of 30. And then you add up these three, and that gives you the total, which according to the letter grade system established by the college, that would be equivalent to a B grade. And typically what I would do, I've been doing this for the past couple of years, is that based on the total score obtained by the class, I would take the highest score and round it up to 100 and curve the other scores appropriately, or accordingly, I should say, all right? So that's another thing that should help you, especially for those of you who might be borderline between two grades at the end of the semester. Okay, now these letter grades actually mean something in terms of what you would have gained from the course. So as stated here below, a grade of A in this course will imply that the student has mastered the full range of topics covered in the lectures and can very successfully apply these to solve the problems presented. The student can derive the important factors that lead to the best solutions and make particularly insightful contributions to class discussions, all right? And then you see some other descriptions for the other letter grades. And I want to take some time out to talk about the I grade, because this has been a source of confusion for some students, all right? So as stated here, the grade of I is given in a situation where a student is unable to complete the coursework for some reason beyond the student's control. So, you know, it could be something like illness, or your house got burnt down, or something like that. In those situations, then I would give that student the I grade, which means basically that the student has not completed all the coursework, but the student will be given time to complete the rest of the coursework. And after that, then that I grade will be replaced by the grade that the student would have actually earned, all right? Now, everything, of course, have to be documented. So for example, if you had to be absent because of some illness, then of course, some medical documentation would be required. You know, if your house got burned down, then pictures and, I don't know, insurance information, I guess, or whatever, would be required in order to establish that happened, all right? And everything has to be above board when it comes to this, because as you can see here, this I grade is subject to the approval of the dean. So basically you have to furnish me with the documents, and then I have to pass that on with some other documents up the chain of command, so to speak, up to the dean, and then the dean would approve the I grade. And then sometime after that, and I don't remember exactly how long, but sometime after that in the next semester, there's a time window for you to complete the rest of the coursework, all right? And all of that will be established, of course, then, all right? So that is something I felt I need to explain to you guys, because in the past, I've had situations where a student at the end of the semester, not liking what his or her grade is shaping up to be, would come to me asking for an I grade. The I grade is not given in those situations where you're not satisfied with what your grade is shaping up to be. The I grade is only given in the situations I described earlier. For some reason that you're not able to complete the coursework, which can be verified. Okay, continuing, let's look at examinations and assignments. Exams will cover material from lectures and assignments. These exams will be primarily problem-solving oriented. Assignments will be usually posted in the Canvas system. I'll show you where those are located and are due on the date specified. And I mentioned this before, and I'm stressing this again. This must be completed by hand and either submitted in person or via Canvas. Now, since this is an online environment, I'm expecting all your assignments and tests to be submitted online, all right? As stated earlier, and I'm stressing this again, if you decide to submit your assignment in Canvas, please ensure that the assignment is submitted as a PDF file. Also, and this is very important, make sure that your name is written on every page. And I guess I repeated it again for emphasis. Anyway, so that's very important. Make sure that your assignment, test, whatever you're submitting to me, is submitted in a PDF format, and make sure that your name is written on every page. And the reason for that is because when I'm printing these documents out on the printer, sometimes the printer acts up and the document or the pages are not printed in order. So therefore, if you write your name on every page, then I know for example, what papers or what pages would belong to a particular student. So make sure that you write your name on every page. Okay, and then below that you see basically the outline of the course. And I'm going to try to be as faithful to the schedule as is possible. But as you can imagine, again, life happens. And as stated here, due to unforeseen happenings, I might find it necessary to make changes to the schedule. And I'll try to be as fair as possible. And I'll give you a heads up when such changes are made. Okay, college policies, academic integrity. We all know, I hope, that cheating and or plagiarism is, of course, not allowed, and if discovered, may result in a special grade known as FF for the course. Now, what that FF designation means is that basically you fail the course as a result of a violation of the Code of Student Conduct with regards to cheating and plagiarism. Now, that grade can be replaced by the grade that you'll eventually earn if you attend what is known as an academic integrity seminar. And there's a charge for this 2-hour seminar. I don't remember what the charge is, but your attendance is required. If you fail to attend that seminar, then the FF grade will remain on your transcript. But as I said before, if you attend that academic integrity seminar, then that FF grade will be replaced by the grade that you'll eventually earn. All right, so that's something that you need to be aware of. Okay, next thing is, if you're a student who has any form of disability, excuse me for a minute. It's very important that you immediately contact the Office of Disability Services. And the way this works is that when you go there, they determine, what your particular disability is, and they will pass on to me information concerning the type of accommodations I need to make for you. All right. So again, everything has to be above board. You cannot just come and tell me that you have a disability. You need to contact that office. Now, it says here contact Victoria Colelli, but she's not with us anymore. And I'm not sure if they hired her replacement, but you can call the phone number provided, as you can see here, for further information. All right, or there's a web page as well that is provided as well. So you can check that out to get more information concerning how you go about getting accommodations for you if you have a particular disability. Okay, equal access, equal opportunity. The College of Central Florida does not discriminate against any person on the basis of race, color, ethnicity, religion, gender, age, marital status, national origin, genetic information, or disability status in its programs, activities, and employments. And if you have any further questions concerning the college's non-discrimination policies, you may contact Carol W. Smith. She's the equity officer, and her contact information is provided. Classroom decorum. Well, we're in an online environment, so in terms of disruptive behavior, I don't think there's anything much to say, excepting that, make sure that when you turn on the camera, make sure that you're presentable, dressed appropriately. And I would suggest that you remain muted unless you have a question to ask, because sometimes background noises can interfere with the conductance of the class. So that's basically pretty much all I can think of in terms of what I expect of you with regards to classroom decorum. All right. The CF Student Assistance Program. Now, this is a program that it's basically a counseling program, I would say. The way this works is that if you have personal issues, problems that interfere with your home or school life or work life, whatever, then you can call this toll-free number. Now, this is a program that is managed by an HMO called Baycare Life Management. And as I said before, you call this toll-free number between the hours of 8:30 a.m. to 5 p.m., Monday through Friday, all right? And that will put you in contact with a therapist on duty, and he or she will be able to help you from that point forward. If you call outside of those hours, then basically what will happen is that the therapist on duty will be paged and he or she will promptly respond to the call. And again, we'll be able to assist you that way. All right. So, if you find yourself in need of this kind of help, I would strongly recommend that you take advantage of it. All right. Because it will go a long way in terms of helping you to have a successful academic career here at the college. All right. Withdrawal. If you want to withdraw from this course, make sure that you fill out the appropriate forms. And I think, I know that at least one form has to be signed by yours truly. And that's very important because in the past, I've had to actually fail students. And I don't like failing students, but I had no choice because sometimes what happens is that some students will just stop coming to class without going through the proper channels. And at the end of the semester, when I'm ready to enter the grade, I have no choice but to enter the grade that they would have earned up to the point where they last attended class. So if you have to withdraw from this class, and let me just say this, I hope nobody withdraw from this class. I want everybody to succeed. I want everybody to be here at the end of the semester. And if you need any help, please see me. You can contact me via Skype or you can email me and I'll do everything I can to help you to succeed in this class. But I understand that in some cases, nothing would help depending on your circumstances, and therefore you have no choice to withdraw from the class. And if that's the case, then please do so properly so that you don't end up with your GPA being hit negatively as a result of simply not coming to class without withdrawing properly. All right. Okay. Next thing I want to talk about are the important dates. And as far as holidays are concerned, I think the only holiday that will affect us will be Memorial Day, which is a Monday. Classes end on the 23rd. And I have to submit the grades by 10 o'clock on Thursday, June 24th. All right. The college reserves the right to evaluate individual cases of non-attendance. Ouch. Sorry. The students should be alerted to the fact that 1, withdrawals do not count in the CFGPA and may not be viewed favorably at the university level or for financial aid. 2, a withdrawal counts as an attempt under the forgiveness/withdrawal policy and the course of P policy. And 3, there are increased costs to take the course on a third attempt. If I'm not mistaken, if you take the same course on the third attempt, you'll be paying full out-of-state tuition for that course. Okay, and 4, there may be a reason a withdrawal request may be denied. And for further information, you may see the college's withdrawal procedures. All right. And then the last page, I like to call it my CYA document. And you all know what CYA stands for, right? Nobody knows? Okay, well, CYA stands for cover your ass. All right. Well, actually, this is to cover my ass because basically what this document is saying, if you sign it, that you have read and understand information in the syllabus and the grade which I must achieve to pass. All right. So I expect every one of you to complete this document and make sure that you email it to me again as an attachment. In fact, as a PDF attachment. So make sure you send that to me ASAP. All right. And that's basically all I have to say as far as the syllabus is concerned. Okay, so are there any questions? Any questions? Any questions?
I have a question about attendance. I normally am working during this time, so I would prefer to probably watch the YouTube videos after the fact when I'm off work. Is that going to be okay?
Yeah, that's fine, especially since you have told me now. So I appreciate you telling me that. And generally speaking, if you can't make it to a class, for the rest of you guys, you can let me know so that I'm aware that you're not just skipping class for no good reason. All right. Okay. Any other questions? Any other questions? Okay. So, sorry. Yes, sir.
I imagine that the dates are going to change, but the other day I was looking at the assignments that were in the, it's like assignment 1, assignment 2, so on, and I noticed that they were all marked as being due on the 16th.
Oh, okay.
Obviously, I imagine that's not the case,
Exactly. Yeah, all of that will be changed, right? You see, what happens is that in creating this Canvas shell for this course, I migrated a lot of stuff from previous courses. So the dates that you see there would be applicable to past semesters. But I'm going to change all of that, as the semester progresses or as this
All right.
course progresses. All right. Okay. Any other questions before I proceed to our first chapter?
Yeah, I have a question.
Yes, ma'am.
So like, are you going to post all the assignments like already on there, or are you just going to post the assignments like every time we have a lecture?
I'm going to post assignments every time I cover a certain amount of topics. I try to give, how should I put this? I try to not load up the assignments too much in terms of the number of topics. So when we get to a particular, like for example, I anticipate that the first assignment will cover chapter 1 because chapter 1 is relatively a short chapter. Chapter 2, I may have 2 assignments for that chapter and so on. It depends on the chapter, basically. So I'll be providing, an assignment after I cover, when I feel as if we cover enough material to create an assignment for that, for that particular material in a particular chapter.
Okay. Also, so
Mhm.
I had you for intro to chemistry.
Oh, really? Oh, okay. I don't remember the name.
Do I have to, I don't have to make another Skype account, right?
No. Just send me a message reminding me that, that,
Okay.
you're in my class and I'll make a record of that.
Okay.
Mhm. Okay, any other questions? Okay, so let's move on to chapter 1. And let me just say here from the outset that I would say that the first 5 and part of chapter 6, the first 5.5 chapters, let's put it that way, I'll be going through them relatively fast, quickly, because a lot of stuff covered in those chapters you would have covered already in your introductory chemistry course, all right? The only difference is that the questions themselves, based on the chapters, will be a bit more challenging. But in terms of the basic concepts covered, it's pretty much the same thing that you would have covered in your introductory chemistry course. So just to give a heads up that I'll be going through chapters 1 through 5 and part of chapter 6 rather quickly. After that, I'll tend to be a bit more slower and more deliberate when it comes to going through the remaining chapters in this course, all right? Okay, so with that said, let's delve into chapter 1. And as you can see here, chapter 1 deals with the concept or the topic of matter and measurements. So just some general information here about chemistry and its applications, right? As I'm quite sure you're aware by now, chemistry is a very wide and dynamic field. And as such, it provides information and materials which affects us in our everyday lives. And in most cases, we benefit from it. So just to give you a simple example of a substance which we benefit from, chlorine, right, is a gas. And as stated here, it has many chemical applications. It can be used, for example, as a disinfectant in bleach, also a disinfectant in swimming pools, and other applications, all right? So that's just one example. And, I'm quite sure you can think of other examples of chemicals that we use in our everyday lives.
Excuse me.
Yes, sir.
If you are, you're not sharing your screen right now.
Oh, it's this. Okay, let me see here. Sorry about that. Sometimes that happens for reasons that
It's all right.
I'm yet to understand. I think when I move from like one document to another, that happens for some reason. Okay, can you see my screen now?
Yep, all good.
Okay, good. All right. Yes, folks, don't be afraid to let me know if things are not showing up on the screen or if you can't hear me or whatever, all right? Because I'm still learning this Zoom thing. Just when I think I've gotten a handle on it, then I learn something else about it, which I need to know. Okay, so as stated here, The application of chemistry, much like the science itself, undergoes constant and I would say rapid change. All right. Every year, there's new information about a different substance. And also every year, there are new substances that are used to better our lives in medicine, pharmacy, agriculture, etc. So what is chemistry? Well, chemistry is a study of matter and the changes it undergoes, right? And in chemistry, we are concerned with, firstly, the composition. In other words, the makeup of a particular substance, all right? So for example, water we know is 2 parts hydrogen and 1 part oxygen, especially at the microscopic level. The water molecule contains 2 hydrogen atoms and 1 oxygen atom, all right? So that's one thing that we're concerned with when it comes to understanding materials and matter. The other thing that we're concerned with in chemistry is the structure. How is the particular substance assembled, especially at the microscopic level? So again, in the case of the water example, we now know that the way the water molecules is structured is that you have an oxygen atom, which is simultaneously bonded to 2 hydrogen atoms, all right? And that, of course, understanding helps us to understand the properties displayed by water and the reactions that water undergoes, all right? And speaking of properties, that's another thing that we're concerned with when it comes to substances. When we talk about the properties of a substance, we're talking about those distinguishing characteristics. So we're talking about things like the boiling point, things like the density, things like the type of reaction that the substance will undergo, all right? So for example, in the case of water, water has a boiling point of 100 degrees Celsius. So that statement is a statement of one particular property that is displayed by water. Water also has a density of approximately 1.00 grams per mil, all right? And so on and so forth. So these are the things that we're concerned with when we're studying chemistry, all right? And we try to look at the relationship between these different factors, right? We look at, for example, how the structure of water affects the properties that it displays, all right? And we're going to look at that in more detail. I think in chapter 8 or 9 is where we're going to discuss the type of intermolecular forces that exist within a substance. Okay, so as you can see in this particular diagram, chemistry is at the heart of a lot of other fields. So that's why we in chemistry, we call chemistry the central science. And of course, being the biased person I am, I think that chemistry is the most important science, which is demonstrated by this particular diagram. Because as you can see here, chemistry affects a lot of other fields. For example, there is a direct relationship between chemistry and physics. One could possibly say that physics and chemistry are basically close cousins, all right? Chemistry also is related to engineering. I don't know if anybody here is majoring in engineering, but you should know that in order for you to major in engineering, you have to do at least, if I'm not mistaken, chemistry 2, all right? General chemistry 2. Chemistry is also important when it comes to the forensic sciences, when it comes to nutrition, when it comes to electronics, materials, medicine, toxicology, of course, pharmaceuticals. So basically, chemistry is very important and relates to almost all the sciences. In fact, all the sciences have some sort of relationship between themselves and chemistry. And even when it comes to non-scientific fields, such as law and business, chemistry is related as well, all right? So chemistry is, as I said before, in my opinion, the most important science. Pretty much a lot of things would not be accomplished by mankind if we did not have a separate field of chemistry. Okay, so let's talk about some key ideas. And again, as I said before, a lot of this would be something that you'd have covered already in your introductory chemistry experience. So the first thing we're going to talk about is matter. What time is it? 9:41. Okay, so matter. What is matter? Matter is anything that has mass and occupies space, all right? In other words, anything that has mass and volume. Atoms, you should know this, it's the smallest distinctive unit in a sample of matter. And of course, molecules are basically a collection of 2 or more atoms held together by covalent bonds, all right? And molecules can be very small, and then you can have much larger molecules such as glucose, sucrose, proteins, etc. Properties of matter. Well, the properties of matter can be placed in two categories. You have what are known as physical properties, and you have chemical properties. So as stated here, the physical property or a physical property is a characteristic that is displayed by a sample of matter without undergoing any change in its composition, right? So basically any characteristic that you can observe without the substance undergoing any chemical reaction would be a physical property. So one example here given is color. So can anybody tell me any other examples of physical properties of matter? Anybody? Any examples you can think of? Doesn't have to be complex, complicated, or anything like that.
Texture.
I'm sorry?
Texture.
Texture. Okay, yeah, that's okay. I would agree with that. Any other physical property you can think of?
It's been a
This
while,
shouldn't be
so
too
I
hard,
may be.
folks.
It's been a while, so I may be incorrect on this, but malleability.
Okay, malleability. Yep. Any other? Let's go for two more.
Then I forget what the word is for it, but I believe the example image usually involved it being formed into a wire.
Oh, so you're
Yes.
talking about ductile.
I can never remember that term.
Okay. One more. Yeah, ductile. That means that, and that applies to metals. They can be drawn into wires. Okay, one more example. One more example of a physical property.
Melting point.
I think that would
I'm
be
sorry?
chemical.
Melting point.
I didn't hear that. I'm sorry.
He said
Melting
melting
point.
point.
Exactly. Okay, very good. All right, so those are examples.
Oh.
Yeah, I heard that. Yeah. Thank you. So those are examples of physical properties because in each of those cases, we're talking about making an observation of a substance without the substance undergoing any chemical change. Now, that is different from chemical properties because these are properties or characteristics which, when observed, involves a chemical reaction that the substance will undergo. So one example that is given here is flammability, right? The fact that something burns, because when you're burning something, you're basically facilitating a reaction between that substance reacting with oxygen from the atmosphere, all right? And that will give you what we call combustion products. So that's one example of a chemical property. So can anybody give another example, maybe two examples of chemical properties displayed by substances? Anybody? Again, this should not be complex.
Sorry about that. I was sneezing a bit. I'm not sure if this is an actual one, but would oxidation be one?
Yeah, oxidation generally would be a chemical property. And in fact, and I was hoping one of you would say this, the rusting of iron, right, is an example of an oxidation reaction. And that's a chemical property displayed by iron. Iron, when exposed to moisture and air, over time will undergo rusting. And rust, that substance is actually a new substance known as iron 3 oxide, formed as a result of the reaction between the oxygen and the iron, all right? So oxidation is a chemical property displayed by some substances, and the rusting of iron is one example of that. Okay, can you come up with one more example of chemical properties, a chemical property displayed by a substance? Come on, one more shouldn't be too hard. Hello, anybody? One more example.
Acidity.
I'm sorry?
Acidity.
Okay, I would go with that. Yeah, I'll go with that. Okay, that's another example of a chemical property. Okay, so with that said, this picture here basically demonstrates the difference between physical and chemical properties of two different substances. To the left in this dish, you have some copper pellets that are in this dish. And if you examine them closely, you'll see that copper as a metal is shiny and it's, it has a kind of reddish color. So the fact that it's reddish and shiny is a statement of one particular physical property of copper. And then on the right side of the dish, there's a substance, ethanol, that is present here. And you see that it's ignited, right? So you see the flame shooting up. So basically what's happening here is that the ethanol is undergoing combustion. And that's basically an example of a chemical property that is displayed by ethanol, all right? So that's basically what this is demonstrating. Okay, so this table here, is there a question?
I got one more that I can say for a chemical.
Oh, yeah, sure.
I'm surprised I didn't think of this right away. Reactivity.
Well, yeah, generally speaking, reactivity is chemical property displayed by different substances, yeah. Now, this table here, again, is demonstrating or showing you some examples of physical and chemical properties. The top half or the top part here deals with physical properties, color, odor, solubility, hardness, and electrical conductivity. Now you'll notice when it comes to physical properties, and you may not have learned this in your introductory chemistry class, there are two types. You have what are known as qualitative properties, physical properties, and quantitative. And the difference between them is that in the case of quantitative properties, you can actually measure them, right? So we're talking about examples such as mass, temperature, melting point densities. These are all measurable quantitative properties. The top part here deals with the qualitative physical properties, which can be measured, they can be observed, but you cannot put a number to them. Things like color, odor, solubility, as we said before. So some examples are shown here, such as sulfur is yellow, hydrogen sulfide stinks, table salt dissolves in water. These are all examples of physical properties that are qualitative, whereas down here, the melting point of lead is, for example, 327.5 degrees Celsius. That is a physical property that can be measured, right? So we call that a quantitative physical property. And then the bottom part of this table, let me move this thing here up here. The bottom part of this table here deals with chemical properties, which, as we said before, are those properties that can be observed. But when they're observed, the substance is undergoing some change. I mentioned the rusting example already. Other examples include sodium reacting violently with water to form hydrogen gas and sodium hydroxide, and nitroglycerin explodes when detonated to give a mixture of gases, all right? So that's basically, showing you the different types of properties and some examples. Okay, so with that said, let's move on to a related topic. Hold on, wait a minute, what time is it? Okay, tell you what, let's take a break. So 10 minutes and we'll get back here, all right?
Hey, Professor Nicely, I need to
Yes, sir.
get to work. Could you send the link to the YouTube so I can catch the rest of the lecture later?
What I'm going to do is I'm going to post the YouTube link in the module section. I'll explain how that is done shortly.
Okay.
In fact, when I get back, I'll show you how to do that.
Or could make an announcement that links to the channel that you put it onto.
What's that?
Could make an announcement that has a link to the channel that you post it to.
Yeah, well, yeah, I can do that too. Yeah. Okay, I'll be right back. Okay, can you hear me?
Yes.
Okay, just checking. And can you see my screen?
Yes.
Yes.
Okay, good. All right. So, related to what we just discussed with respect to physical and chemical properties, we have what are known as physical and chemical changes. And if you understand what we just discussed, then there should be no problem, because this is basically along the same lines in terms of the changes that substances will undergo. So physical changes basically involves a change in the appearance of a substance without a change in the composition or structure. So for example, the sublimation of ice in winter. I don't know if you know what sublimation is, but sublimation is a conversion of a solid to a gas without going through the liquid state, all right? And that is an example of a physical change, because if you're starting off with ice, which is H2O, and it undergoes sublimation to form a gas, the formula for the gas is also H2O, right? So the structure of the molecules, either in the solid or the gaseous state, is still one oxygen atom bonded to two hydrogen atoms, all right? So that's basically what we mean by physical change. And there are other examples of physical changes, such as, you know, when you add salt to water, again, you know, there's no chemical reaction taking place. The melting of ice is another example. So those are just some examples of physical changes. In all these examples, there is a change that can be observed, but the composition and the structure of the substance does not change. Then we have chemical changes. Okay, why is this thing not responding? Okay, right. So chemical changes is where a change can be observed, and at the same time, you're going to have a change in the composition or structure of the substance. So for example, the spoilage of foods, the rusting of iron, pretty much any chemical reaction that you can think of, those are examples of chemical changes, all right? Okay, so now we're going to get into a discussion of matter and the classification of matter. And again, this is something that you should have met before. First thing we need to talk about is, well, I think we defined it before. I'm going to define it again. Matter is anything that has mass and volume. So any material that you come across, basically it's made up of matter. Now, when it comes to the classification of matter, you can have, let me go back to the previous slide here. You can have matter being categorized into these two separate categories. You have substances, and then you have mixtures, right? So what we're going to look at is this part of this diagram here, because as you're going to see, substances as a group can be further subdivided into two other categories, elements and compounds. All right, so we're going to look at this firstly, and then we're going to look at this part of the diagram after that. So as we said before, matter is anything that has mass and volume. And as far as pure substances are concerned, it's basically a type of matter with a fixed composition, which does not vary from sample to sample. All right, so a pure substance would be something like water, right? The composition is fixed, 2 parts hydrogen, 1 part oxygen. And there's no variation from that for that pure substance, all right? So as I said before, substances can be categorized or subcategorized into elements and compounds. So let's talk about the difference between these two. Elements are basically substances that cannot be broken down into simpler substances by chemical means, while compounds are substances that can be broken down into simpler substances by chemical means, or another way of defining it, a substance made up of 2 or more atoms of different elements, and the combination of these atoms are in fixed proportions, all right? So that's the difference between elements and compounds. And I'm quite sure we can think about examples of elements. In fact, if you have access to our periodic table, that's basically the comprehensive list of elements. And we're going to talk more about the periodic table, why the elements are arranged in the way they are arranged in that table. And compounds would include substances such as sodium chloride, glucose, sucrose, what else? Acetone, alcohol or ethanol, and so on and so forth. So those are all examples of compounds. Then as far as the other side of that diagram is concerned, we have mixtures, all right? Which is the other category that we can identify among the broad group of substances. So the definition of a mixture is that it's a physical combination of 2 or more substances. And what you'll find that is characteristic of mixtures is that it has no fixed composition, all right? So for example, you could have a mixture of, let's say, ethanol and water. It could be a 50-50 mixture, or you could have a mixture where 25% is ethanol and 75% is water, or vice versa. I mean, there's literally an infinite number of possibilities in terms of the variety of composition of that mixture, all right? So that's one big difference. And let me stress this, one big difference between a mixture and a compound. A compound necessarily must have a fixed composition. Mixtures do not have a fixed composition, all right? So under the broad category or subcategory, well, the category of mixtures, we have what are known as homogeneous mixtures and heterogeneous mixtures. So a homogeneous mixture is also known as a solution. And it is a mixture where the composition and properties are uniform throughout that mixture, all right? So for example, if I were to mix together ethanol with water, right? Basically, you will not be able to make a distinction in that mixture between the two because they will be equally distributed between themselves in that situation, all right? And if it's a 50-50 mixture, then that 50-50 composition will be the same right throughout the substance. So if you could take a sample at the top part of that mixture, in the middle and at the bottom part, and analyze it, you'll find that it's a 50-50 composition, all right, right throughout. So that's basically what a homogeneous mixture is. Now, a heterogeneous mixture is one that is not uniform, all right? In fact, one would be able to make distinctions between the components of that mixture. So for example, oil and water is a good example of a homogeneous mixture. Let's say you're mixing vegetable oil with water. So if you add water to vegetable oil, eventually what you'll see is when everything settles out, you're going to see the oil settling at the top and the water at the bottom, all right? And that's because the water is more density than the vegetable oil. And you'll see basically that you can distinguish between the oil and the water in that mixture. So that's an example of a heterogeneous mixture. Okay, what else? So let's talk about chemical symbols. Again, this is something that you would have met before in your previous chemistry experience. And you should recognize that basically the chemical symbols are 1 or 2 letter designations derived from the name of the element. Now, most of the symbols are based on the English names, and these are just a couple of examples: H for hydrogen, Ne for neon, and Cr for chromium, all right? And note that in the case of neon and chromium and other symbols made up of 2 letters, the first letter is always capitalized and the second letter is always lowercase, all right? Now, if it's 1 letter, then that letter would be uppercase, all right? Now, there's some symbols that are not derived from the name of the element in English, but from the Latin names. So for example, in the case of copper, the symbol for that element is Cu, and that's because the Latin name is cuprum. The symbol for gold, the symbol for gold is Au, and that's because it's derived from the Latin name, I don't know how to pronounce this, aurum. And these are some other examples as well, all right? So, you know, not all the names have an English origin, some are from a Latin origin, all right? Okay, let's move on now, and this might be a bit of a departure from chemistry specifically, but this applies to pretty much all the scientific disciplines. We're going to talk about the scientific method, which is basically the method that is used by scientists worldwide to understand how nature works. And of course, you know, it applies not only to chemistry, but applies to the other sciences as well. So the first step of this process is the observation. And this is where your senses come into play, your sense of smell, sight, touch, even though in chemistry we try to not, you know, touch chemicals and so on. But these are basically what is observed by your senses, all right? In some cases, what we observe can be measured. And basically, if we can see some consistency in terms of the observation, we can basically state it as a natural law, all right? So for example, and we're gonna meet this later on in chapter 5, I think, Boyle's law states that the pressure of a gas is inversely proportional to the volume, right? So that's an observation that is made over and over and over again without any exception, right? If you try to reduce the volume of a gas, the pressure will proportionally increase and vice versa, all right? So that's an example of a natural law. Now, when it comes to the scientific approach, after you have done the observation part of it, which is the first step, then you develop what is known as a hypothesis. And basically a hypothesis is a proposal, a tentative proposal that explains what is observed, right? Now, of course, this proposal has to be reasonable, right? So you can't say anything like, you know, something magically happens or whatever, all right? You have to put forward a reasonable explanation that explains the observation. Of course, we don't stop at that point as scientists because we now need to find out whether or not the observation or the explanation that is given in the hypothesis is in any way true. So basically we have to subject the hypothesis to a test, or I would say more than one test. Now, in the case of the natural sciences, we do that by performing experiments. And this is probably where the hard work of the scientists is most challenging. Primarily because you have to basically design an experiment so as to test the hypothesis to see if the hypothesis will fail. In other words, you want to see if the hypothesis is falsifiable. So basically the design of the experiment must be such that if the hypothesis is not true, then the experimentation will show that, that it will fail, the hypothesis will fail, all right? Now, you'll notice that there's an arrow going back from the experiment to the hypothesis. And that happens over and over again, especially during the earlier stages, because very often what you'll find is that in the initial stages, the data or information obtained by experimentation the first time around will not be in harmony with the hypothesis. So when that happens, what you'd have to do is come back up here to the hypothesis and make changes to it, or basically replace the hypothesis with a new one. And then you subject that to testing by experimentation again. And this happens over and over and over again until you get some harmony between the experimental data and the hypothesis. And when you achieve that harmony, then that hypothesis is now called a theory, all right? So as stated here, a theory is a set of conceptual assumptions that explains the data from accumulated experiments. And this is very important to understand the distinction between a theory and a hypothesis. Remember, the hypothesis is a tentative explanation of what you observed in the first step. The theory is an explanation that is backed by the weight of the data through repeated experimentation, all right? Okay, so once we achieve the theory, that does not necessarily mean that that would be the end of the story, because the theory itself can be subjected to further experimentation, further testing to see if it can stand up to further scrutiny. Now, what you'll find is that in the history of science, there are many instances where you'll have a theory that has been developed, going through the steps as I have outlined. And what you'll find is that the theory might persist and be, believed by scientists for a long period of time. And then out of the blue, somebody somewhere will come up with an experiment which would basically prove the theory not to be true, which means that if that happens, then you have to come back up here to come up with a new hypothesis and go through the steps as we talked about before, right? So this is very important for us to recognize that as a result of what I just said, the fact that further experimentation will take place or can take place to demolish a theory, that science is a dynamic field. There are no sacred cows in the sciences. Everything is subject to testing and questioning. And when a particular theory fails experimentation to test it, then we don't hold on to the theory for dear life. We get rid of it and we basically develop a new theory. And that theory is also subjected to testing and so on and so forth. All right. So there's always that kind of activity taking place where new information is developed and new theories are developed as a result of testing the older theory. And my favorite example of this is, and unfortunately I forgot my writing tablet, so I can't really write it and show you, but way back when, and I don't remember the dates for these things, but way back then in those days, there was a theory that was believed by scientists known as a vitalistic theory. And basically what this theory says is that there are certain substances that exist in nature that cannot be man-made. They can only be made in nature because there's this thing out there in nature known as a vitalistic force, which is necessary for the making of these natural compounds. All right, so that was the belief in those days. All right. And then a scientist, a chemist by the name of Frederick Waller, he accidentally discovered a way of making a compound known as urea. He was actually trying to make another compound, ammonium cyanate, but in his effort to make that compound, he ended up accidentally making urea in the lab. Now, I don't know if you guys know what urea is, but urea is a chemical, a compound that is found in the urine of mammals, cows, human beings, pigs, goats, etc., right? So Frederick Waller was the first person to demonstrate that compounds that, at least in the case of urea, a compound that is made by nature can be made in the lab as well, synthetically. And since then, other compounds that have been found in nature have been made in the lab. And this is something that happens almost routinely nowadays, all right? So that's an example of a situation where a theory has been established, accepted by the scientific community, and then out of the blue, somebody comes up with data or information based on experimentation to show that the theory is not true, all right? And that's just one example. And there are other examples in the scientific history where that has occurred, all right? So that's basically the scientific method. There's one more thing I want to say and stress about the scientific method. And this is very important, especially if you plan to pursue a career in the sciences, all right? Now, if you recall, I said that after you come up with your hypothesis, you test your hypothesis by running an experiment designed to demonstrate that the hypothesis will fail if it's not true, all right? And if you remember, I said that if there's no harmony between the experimental data and the hypothesis, then you have to go back to the hypothesis and make changes to the hypothesis to fit the data that you obtain. And that is very important. You make changes to the hypothesis to fit your experimental data. You do not make changes to the experimental data to fit the hypothesis. That is called, in my book, scientific malpractice. And the consequences of that could be severe, including negatively affecting your career. And in some cases, even jail time, all right? So I'm saying that to say that whenever you're doing any experiment, and it doesn't matter if it's an experiment at this level or in a major research facilities or in an academic lab, it's very important that you exercise integrity and honesty in your work. And therefore, you should not make any changes to experimental data to fit some preconceived notion of what you think the results should be, all right? Okay, so that's basically all I have to say concerning the scientific method. Okay, are there any questions on this? Any questions on the scientific method? Any questions? Okay, so let's talk about the use of models. Now, models are very useful depending on the level of chemistry and what you're trying to understand about molecules. As stated here, they're tangible items or representative pictures of atoms and molecules. So what you see here on the screen is an example of a model of the water molecule. And this particular model is called a space filling model because it gives you an idea, a picture of how the sizes of the atoms are relative to each other. So the red sphere represents the oxygen atom and the white spheres represents the hydrogen atom. So this represents the water molecule. And these green spheres here represents the chlorine atom. And as you see here, the chlorine molecule consists of 2 atoms of chlorine, all right? So this is one type of model. There are other types of models later on, but just to let you know that models are useful for representing molecules, especially in the 3-dimensional arrangement. Okay, scientific measurements and units. So we're all familiar with, measuring things, not only in the lab, but even in our everyday lives. You measure the weight of something or the length of something. And with every measurement, there are 2 parts. You have what is known as the quantitative piece, and then you have the qualitative piece, all right? The quantitative piece, of course, would be the numerical part, and the qualitative piece would be the unit. And it is totally meaningless to express any measured value without these 2 together, right? So you can't just put the number, you have to put the unit as well, all right? So for example, if we're talking about somebody being paid wages, and you want to say what the wage is, it's not enough for you to say 60, right? You have to give the associated units because of course there's a big difference between $60 per week and $60 per hour. Of course, which is preferable would be the $60 per hour, all right? So, the units is very important in terms of conveying the information about what we're actually talking about with respect to a measured value. Okay, so these are the different units of measurement in the SI system. SI is a French abbreviation for International System of Units. You have the unit of length, which is a meter unit, the unit of mass, which is a kilogram unit, the unit of time, which is second, the unit of temperature, Kelvin. For the amount of substance, the unit is mole. And then these 2 last ones we won't be using in this chapter, but I'll mention them anyway. Electric current, the unit is ampere, and luminous intensity, the unit is candela, all right? So in this chapter, we'll be using the first 5. In this course, we'll be using the first 5. In General Chemistry 2, you'll be introduced to the unit of electric current when you get to the topic of electrochemistry in general chemistry 2, all right? And for those of you who have to do physics, or if you have done physics already, then you would have already been introduced to this particular unit, all right? But for this particular course, we'll be using these first 5 units. And over here are the symbols for those units, all right? Now, in addition to the basic metric unit, we have what are known as prefixes, which express larger or smaller versions of those units. Now, this table that you see here is a very abbreviated table. There's a more comprehensive table. Let me show you where that is located in Canvas. In fact, I just remembered I promised to show you where things are located in Canvas. So let me do that now as a bit of a break from what we're discussing. Now, the tables that you'll be using in this course will be located in the tables folder here. So if you click on that, what will come up would be certain data and tables that you'll be using pretty much throughout this course. I would say this one here, this link is the most important because it gives you several pages of information, including the periodic table. So let me just download this and show you what it looks like. Okay, so let me make this full page. Okay, so basically, as you can see, we have the periodic table of elements here. We have another version of the periodic table of elements here. And then I decided to include this. This gives you a list of the elements alphabetically. And then we have this chart here, which gives you the ions, the common ions. Another chart which gives you the common ions that you'll be using. And a third chart with the common ions. Now, the page I want to scroll down to is the one that gives you the prefixes, the metric prefixes, which is this one right here. Let me turn it right side up. Okay, so these are the metric prefixes. Deci, the symbol is D, and the actual numerical value associated with that prefix is 0.1 or 10 to the minus 1. You have centi, you have milli, etc., right? So these would convert the fundamental metric unit to smaller values. And then these here would convert the fundamental metric units to larger values. Geiger would be 1 billion, mega would be 1 million, kilo is 1,000, and so on and so forth, right? So those are the metric prefixes that you'll be using in addition to the metric units. Let me go back to this here. Okay, so that's as far as the prefixes are concerned. Hold on. Oh, okay. So what I'm going to talk about here, what time is it? Okay, we have enough time. Okay, so what I'm going to talk about here are the different types of measurements, right? And the first one we'll be looking at is volume. Now, volume, of course, is the amount of space occupied by an object. And the volume units would be, for the SI system, the liter unit, right, which is the base unit, all right? And this is very convenient, especially for measuring the volume of irregularly shaped containers. Now, there are some other units of volume which are related to the unit of length, all right? And to demonstrate that, we're going to look at this diagram right here. Now, this diagram basically is a cube made up of smaller cubes that are stacked on top of each other and going in different directions so as to form a larger cube, all right? Now, the length of the edge of each cube is 1 centimeter, right? So that means that the volume of each of these cubes will be 1 centimeters cube, right? Now, to make this larger cube, which has for each edge a length of 10 centimeters, what you'll find is that you're going to need 10 cubes stacked going this way, 10 cubes going that way, 10 cubes going up. So therefore, basically for the larger cube, the volume would be equal to 10 times 10 times 10, which is equal to 1,000 centimeters cube, all right? And it turns out that, well, before I get to that, 1 centimeter cube is also equal to 1 milliliters. So 1,000 centimeters cube turns out would be equal to 1 decimeters cube, right? In fact, let me see if I can write something here. No, I'll be using my mouse to try to do this. So 1 decimeter, whoops. is equal to 10 centimeters. All right. Whoops. Let me erase this here. So this is where is that thing? Oops. Okay, centimeters. All right. So if we cube the 10 centimeters here, so this is cube, raised to the 3. That means we have to cube this as well on the other side, 1 decimeter cube. Right? So basically, the 10 that is cubed here will be equal to 1,000 cm cube, right? So therefore, that's why 1,000 cm cube is equal to 1 decimeters cube. And it turns out also that because 1 centimeters cube is equal to 1 mil, that means that 1,000 centimeters cube will be equal to 1 liter. So those are the kind of relationships that exist between the liter unit, the decimeter unit, the centimeter cube unit, and the milliliter unit. Okay, enough of that. I'll make sure next time, hold on, let me turn this off. I'll make sure next time to remember to bring my writing pad, my writing tablet. Okay, let's talk about another unit of measurement with respect to temperature. What's the noise? Okay, I'm sorry about that. So when it comes to the measurement of temperature, there are a couple of scales that are used. And what you see here on the screen are the Celsius scale, 2 thermometers, one graduated in Celsius and the other one graduated in degrees Fahrenheit, all right? And there's a relationship between the two. They're related by an equation, which I don't see here. Okay, so let me try to write this equation. Okay, so the relationship between the temperature and Fahrenheit is temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius minus 32. All right, I hope you can make that out. So that's the relationship between the temperature in Fahrenheit and the temperature in Celsius. It's 9/5 times the temperature in Celsius minus 32. So based on that relationship, we have these two different scales. And what you'll find, for example, is that 0 degrees Celsius will be equal to 32 degrees Fahrenheit. 100 degrees Celsius would be equal to 212 degrees Fahrenheit. And there are some other relationships between them as well. So that's what's shown here and here, all right? Room temperature, which is about 20 degrees, is equal to, in Celsius, is equal to 68 degrees Fahrenheit. So that's basically the relationship between the degrees Celsius and degrees Fahrenheit. Let me just say that the Celsius scale is based on the properties displayed by water, right? Basically what they did in order to establish the scale is that they defined the freezing point of water as 0 degrees Celsius and the boiling point of water as 100 degrees Celsius. And therefore, based on those two set values, the scale was developed based on that, all right? Now, a third scale, which is used in the SI system, is the Kelvin scale, all right? And the relationship between the Kelvin scale and the Celsius scale Again, let me try to write this down here. Let me try to, where should I squeeze this? Let me squeeze this here. Temperature in Kelvin is equal to the temperature in Celsius plus 32, I'm sorry, plus 273. All right, so that's the relationship between the Kelvin and the Celsius scale. The Kelvin scale is developed as a result of properties displayed by gases, especially in regards to the relationship between the temperature and the volume and pressure of gases. And we're going to get into that later on, all right? Okay, so that's basically a discussion of the different units of temperature. So let's talk about the concept of precision and accuracy in measurements. So, you know, people tend to use the terms precision and accuracy in everyday language as if they mean the same thing. However, in the sciences, there is a difference between them. Now, when we're talking about the precision of a measurement or precision of measurements, we're talking about how close individual measurements are to each other. So for example, let's say I gave each of you the same ruler to measure the length of, let's say, a piece of board, right? And each of you do that measurement independently. Then what you'll find is that there may be some variations, slight variations between the different measured values, right? But these values would be relatively close to each other, all right? So basically what we're talking about is the precision when we're referring to how closely these measured values are to each other, all right? Now, accuracy means something different. Accuracy refers to how close the average of a set of scientific measured values are to the true or correct or most probable value, all right? So again, going back to the example I just mentioned, let's say that I know what the actual length of the piece of board is that you guys were measuring. Then basically the accuracy of your measurements would be how close the average of your measurements would be to the actual length of the board, all right? So that's basically the difference between precision and accuracy. And then there's a third term that is mentioned here, sampling errors, which occur when a group of scientific measurements do not represent the entire population of the variable being studied. And this is oftentimes something that is observed in statistics when you're taking surveys, or if you're looking at the population of, let's say, a particular organism in the forest, for example, in biology. When you're doing those sort of research efforts, you try to make sure that your sample is representative of the entire population, all right? If you don't do that, then you're introducing sampling errors in your research. Okay, so those are just some terms that you need to be familiar with when it comes to sciences in particular, or sciences in general and chemistry in particular. And this is basically a pictorial demonstration of the difference between accuracy and precision. So as you can see here, what we have is a dartboard and 4 different situations where people or a particular person is throwing darts at the board. So the center of the dartboard represents the true value, and where the dart ends up represents an attempt at measuring whatever this person is trying to measure, all right? So in the case of A, where the darts are all over the place, they're far from each other and far from the center, this represents a situation of low accuracy and low precision, all right? In the case of this situation here, this represents a situation of low accuracy and high precision, because in this case, the darts end up close to each other, but they're still far away from the center. Now, in the case of the third attempt here, what you'll find is that the darts are relatively close to each other, but they're still not hitting the center. So this represents a situation of high accuracy. Actually, these darts are not as close to each other as possible, but they're close to the center. So that represents high accuracy and low precision. And then, of course, this is the ideal situation where all the darts are at the center. So that represents high accuracy and high precision. Excuse me. All right, so I hope that clarifies the differences between precision and accuracy. Okay, so the next topic we're going to talk about is what we use to indicate the level of precision in a measured value. And that is we look at the number of significant figures in an expressed measured value. Excuse me 1 minute. Okay, so whenever you take any measurements of anything, doesn't matter if it's mass, volume, whatever, the digits that you end up with will reflect the level of precision, right? And in fact, the more significant digits that you obtain, the better would be the precision of the measured value, all right? So we want to get it as precise as possible when you're taking any measurements, right? So when we talk about the significant digits, we're talking about all those digits in a number that are known with certainty, plus the first uncertain digit, which of course you'd have to estimate, all right? So basically we try to pin down those digits that we know with absolute certainty, and then the digit that we're not certain about, the first uncertain digit, all right? Now, this concept applies only to measured values, right? So what we're going to see later on is that when it comes to numbers that you will be exposed to and that you'll be using in chemistry and other sciences, there are two types of numbers. You have measured numbers, and then you have what are known as exact numbers. So the concept of significant figures will be applicable to measured numbers. When it comes to exact numbers, we consider them to have an infinite number of significant figures, and we're going to talk about that later on. In fact, that's what we say right here, actually. Exact values have an unlimited number of significant figures. And how do we tell the difference between measured values and exact values? Well, obviously, measured values are numbers obtained by measuring something. Exact numbers, on the other hand, are obtained by one of two ways, either by counting or by definition, all right? So if I say, for example, that the number of students in a class is 20, then that number 20 would be an exact number because it's a number that's obtained by doing a head count of the students in the class, all right? You did not pull out an instrument to measure the number of students. You basically count them, and that gives you the number of students. So that's an example of an exact number. Now, that's an exact number by counting. When it comes to exact numbers by definition, one example that comes readily to mind is the relationship between the meter unit and the centimeter unit. 1 meter, let me try to write this down here. 1 meter is equal to 100 centimeter. All right. So this 1 and this 100, those two numbers are said to be exact because the relationship between them is by definition. All right. So what you're going to see is that it's very important that you're able to identify measured numbers and exact numbers in problem-solving exercises, because that will make a difference in terms of how you express your final answer when you're solving these problems. And we're going to get into that shortly. Now, what I'm going to do here is that, well, let me see what the next slide says. Okay, so what I'm going to do here, because I'm not satisfied with the way this particular set of slides explain, okay, what's going on here? Why is this not, okay. I'm not satisfied with the way this set of slides explain the rules for significant figures. So what I'm going to do is get out of this here and go back to a PowerPoint of the introductory chemistry course that I teach here at this college. And I'm going to use this to demonstrate the whole concept of significant figures, and especially when it comes to zeros in measured values. Okay, so as I said before, the number of significant figures, or the significant figures in a measured value, would be those numbers that we know with certainty plus the last digit, which would be the estimated digit. All right, so let's say you're given this number which represents a measured value. Well, what that means, therefore, is that in terms of the significant figures in this represented value, these digits are known that you see here, right? So the first 5 digits are known, and the 6th digit would be an estimated digit, all right? So that's basically how we determine the number of significant figures in a measured value. Now, to illustrate how we determine the estimated digit, we're going to use an example. Okay, well, before we get to that example, here's another example of a measured number. We're certain about the first 5 digits here, and the 0 here at the end would be an estimated digit, all right? Okay, so as I was about to say, I'm going to show you now how do we determine the uncertain digit that is estimated, all right? Or the significant digit that is an estimated digit. So the example we're going to use here is one of reading a thermometer, all right? So as you can see on the screen here, there are 3 thermometers right here. The first 2 has identical scales, right? Where between, for example, the 20 here and the 30 here, there are, how can I get this? Let me try this here. I want to move this out of the way. Okay, all right, let me just put this all the way to the top. Hopefully that helps. Okay, so we have the 20 degrees here, and we have the 30 degrees here, and we have 10 equal divisions between the 20 and the 30, right? So therefore, obviously that means that this mark here represents 21, that's 22, that's 23, 24, 25, etc., right? And the same is true for this scale here. Okay, so let's see if we can determine what value is being measured by the mercury coming up to this point right here, all right? So based on the scale that is etched here, we know that the value being represented here would be 21 point something, right? So the question is, what is that unit after the decimal point, right? So one person could look at this and say, well, I think this is 21.2, all right? In other words, we know the first 2 digits is 2 and 1, but the third digit we're estimating, and based on where it is right here, this looks like this is 0.2 right here. Another person could just as reasonably look at this and say, no, I don't think it's 21.2. I think it's 21.3, all right? Now, as far as I'm concerned, both persons are correct because whereas they have established the certainty of the first 2 digits in the measured value, the third digit at best can only be estimated, all right? So it turns out that in this case, the measured value here would be 21.2 because we are certain about the first 2, we're certain about the 1. What we are not certain about is the 2 after the decimal point, all right? But as I said before, another person could just as well said, this is 21.3, and that person would be just as correct, all right? So that's basically how you determine the uncertain digit. It's by estimation, and it's based on the scale that you're using, right? So that's basically what limits the level of significance or the level of precision of the particular instrument, and that is the type of scale that the instrument has, all right? If you look at the second, oh, and by the way, before I move on to the second scale, the number of significant digits being expressed here is 3, right? We're certain about the 2 here, we're certain about the 1 here. We're not certain about this 2 because we estimated it. So therefore, the total number of significant figures expressed here is 3. Okay, now if you look at the next scale here, you'll notice that the mercury level is up to this mark right here. So it looks like it's exactly on the mark that is shown here, which represents 0.2. So one might be tempted to think that the value being represented here is 22 even, right? But because this scale and this scale are basically the same, then the level of precision that is reflected in measuring this value here should be the same as the level of precision reflected here. So if you think that this is on the 2 line here exactly, or the 0.2 line here exactly, then basically, well, the 2 line here, I should say, then basically the answer here would be 22.0. So you have to add the 0 after the decimal point to indicate the same level of precision as indicated over here in this example. So the answer here would be 22.0 because the 0 here is basically an estimated digit that is uncertain, and therefore you're uncertain about that digit. And therefore the number of significant figures expressed here would be 3 significant figures. Okay, Now, if you look at the third scale, you'll see that it's significantly different compared to the other two, because not only do you have these markings here for the unit values, but you have some smaller divisions between, let's say, 20 and 21. So you have 10 equal divisions. So therefore, what these indicates, each of these lines represents 0.01 degree, all right? And that affects the level of precision that, that this instrument will display. So if we want to indicate what is being measured by the mercury level being here, let me look at this more closely. We are certain that it's 22.1 something, right? So therefore, we are not certain about the second digit after the decimal point. We're certain about the 2 being the first digit, and then 2 being the second digit. Let me see here, 22. And we're certain about 1 being the third digit, which comes after the decimal point. What we're not certain about is the digit that comes after 1. It turns out that this represents 22.11 degrees, but in this case, we're not certain about this one right here, so that would be an estimate. So another person could look at this and say, well, this is 22.12, all right? So that basically would represent the temperature being demonstrated here. And in this particular case, the number of significant digits here would be 4. So basically, based on the scale here, the level of significance or the number of significant figures here would be greater compared to the other two, which means that the temperature being measured here, or the thermometer that is used to measure the temperature here, would be more precise compared to the other two thermometers. So I thought it was important that I go through this particular example so that you understand how the number of significant figures are determined, and most importantly, how the last digit, which is estimated, how that is determined, all right? But remember, the definition of significant digits are all those digits that you can determine plus the last significant digit. Okay, I'm going to stop here again. It's now 10:50. So you can take a break and we'll get back here at 11. Mm. Okay, I am back. I take it you can still see the screen, right?
Yes.
Okay. All right. So, as I said before, exact numbers. These are numbers that you can identify in any question based on whether or not the number is representing the number of items being counted or by definition. So, for example, what you see here are 5 spheres. So that 5 would represent an exact number, all right? And as stated earlier and stated here, the exact numbers have an infinite number of significant figures, all right? That's very important. Again, we're going to see the reason why that is important later. And I mentioned this example in terms of defined numbers. These are also exact. And the example I gave was a relationship between the meter unit and the centimeter unit. Here's another example, the relationship between the inch unit and the foot unit. 12 inches is equal to 1 foot. So the 12 and the 1 in this relationship here are both exact numbers because they're related by definition, all right? So I just reiterating what I said before, when it comes to exact numbers, those are the 2 types. You either obtain the exact number by definition or by counting. Oh, and here's the relationship between the meter and centimeter unit I mentioned before. Again, the 100 and the 1 here would be exact numbers. Okay, so what I'm going to do right now is go through the rules for determining the number of significant figures in a measured value. So in other words, if you're given a number which represents a measured value, let's say you're given a number in a question, then these are the rules you'd follow to find out which of the digits in the given number would be significant and which numbers would not be. Okay, so the first rule is that all non-zero digits are significant. All non-zero digits are significant. So all digits from 1 through 9, if you see them appear in any measured value, those numbers are significant. So here's one example. We have 3 significant figures being indicated here. And that's the first example. Okay, so that's simple, no problem. If it's non-zero, it's significant, all right? Now, the rest of the rules that we're going to discuss has to do with zeros in particular situations. And the first of these rules would be a situation where a 0, or more than 1 0 for that matter, is sandwiched between 2 non-zero digits, all right? So in this case here, 401, these digits, all of them are significant, including the 0, which is sandwiched between the 1 and the 4, all right? So we have 3 significant digits here because this 0 is sandwiched between 2 non-zero digits. Here's another example. And in this case here, we have a decimal point and we have 2 zeros here, right? Sandwiched between a 3 and a 6. So the decimal point does not make a difference, all right? So in this particular case, we have 5 significant figures being indicated here, all right? Okay, next example, 9.03. Again, this 0, which is sandwiched between the 9 and the 3, is significant. So therefore, we have 3 significant digits represented here, all right? Okay, now the next rule has to do with zeros at the end of a number where there's a decimal point in that measured value. So if you look at this particular example here, you'll notice that there are 3 zeros at the end of this number, and there's a decimal point here, right? That decimal point make these zeros significant. So therefore, the total number of significant digits here would be 5, all right? Okay, here's another example. In this case, we have a 0 here at the end, and we have a decimal point here. So therefore, again, this decimal point makes that 0 significant. So therefore, the total number of significant digits here would be 5. Okay, now what we're going to look at is where there is zeros before the first non-zero digit. In this case, those zeros will not be significant. Here's the first example. So you'll notice that there are 3 zeros before the first non-zero digit. So that means that these zeros are not significant. So therefore, there's only 1 significant digit here, which is a 6, all right? Here's another example. Now, in this case here, we have 2 types of zeros. We have this 0 here, which comes before the first non-zero digit, And we have this 0 here, which is sandwiched between the 7 and the 9. So therefore, this 0 is significant. I'm sorry, this 0 is not significant. Oops, I'm sorry. This 0 is not significant, but this 0 is. So therefore, the total number of significant digits here would be 3. Okay. Now here's another rule which deals with zeros at the end of a number where there's no decimal point. According to this rule, the 0 is not significant. So let's look at this example right here. So if you look at this example, there's no decimal point. We have 4 zeros at the end of this number. These zeros therefore are not significant. So therefore there's only one significant digit represented here, and that would be the 5. Here's another example. In this case here, you have 1 0 at the end of this number. There's no decimal point anywhere in this number. So therefore this 0 is not significant, which means that the total number of significant digits here would be 4. Okay, so that basically covers the rules for determining which zeros are significant in a measured value or not, all right? So let me see here. Let me go back to the original collection of slides. Let me skip this here. Okay, so let's talk about the rules for significant figures when you're doing calculations. And this is important because, of course, as you all know in chemistry, we do calculations. And basically, you need to know how to handle significant figures so that you get the correct answer, which reflects the correct level of significant, or I should say the correct level of precision based on the measured values involved in the calculation. Now, the key point you need to recognize whenever you're doing these kinds of operations is that the calculated quantity can be no more precise than the least precise data used in the calculation, right? So if you're doing a calculation involving several numbers, then your resulting answer can be no more precise than the least precise values involved in your calculation. And the reported results should reflect this fact. So the analogy that is used to help to further the understanding of this particular key point is that a chain is only as strong as its weakest link. So just as how the chain is only as strong as its weakest link, the precision of your final answer will only be as precise as the least precise answer or least precise value involved in your calculation to arrive at that answer. Okay, so how do we do this when it comes to calculations? Well, it turns out that the rules are different when it comes to addition and subtraction compared to multiplication and division. So we're going to look at multiplication and division first, right? So when you're multiplying and dividing numbers, the reported results should have no more significant digits than the factor with the fewest number of significant figures. So to illustrate this, let's look at this setup right here, where you're multiplying 1.827 by 0.672 meters, right? So of course, you'd use your calculator to do this calculation. So if you punch your numbers, press the equal sign, then this is the answer that you're going to get on your calculator display, all right? But this would not be the final answer because you have to round off this answer according to which one of these two would have the lowest number of sig figs. So if you look at this number here, 1.827, that has 4 significant figures. If you look at this number here, that has 3 significant figures, which means that your answer here must be rounded off to the level of significance of which is lowest compared to, well, lowest of the numbers involved in the calculation. So that means that you have to round off this answer to 3 significant figures. So therefore the final answer is 1.39, all right? And please note the units. The unit is meters squared because when you're multiplying these two numbers, you're multiplying meters by meters. So the final answer in terms of the units will be meters squared. So that's basically how you do rounding off when it comes to multiplication and division. It's the same idea when it comes to division. If you were to divide this by this, then your final answer would have to be rounded off to 3 significant figures as well. Okay, so that's as far as multiplication and division is concerned. So what about addition and subtraction? So if you're adding and or subtracting numbers, then basically your final answer must be rounded off to the fewest number of decimal places of the numbers involved in this particular mathematical operation. So let's say you're doing this particular calculation. You're adding this number to this number to get this, and then you're going to follow that up with subtracting this number. And when you do that on your calculator, you're going to get this on your display, all right? However, you need to round off this to the correct number of decimal places. So the question now becomes, okay, how many decimal places you need to round this off? Well, you have to look at the numbers involved and see which one has the lowest number of decimal places, and you round off this answer to the same extent. So you'll notice that you have 2 decimal places here, you have 3 decimal places here, you have 4 decimal places expressed here. So that means that you need to round off this final answer to the lowest number of decimal places involved in the calculation, which will be 2 decimal places. So therefore the answer, the correct answer to reflect the correct level of precision would be 112.13, all right? So that's basically how you would do addition and subtraction when you're rounding off to the correct number of sig figs. Okay, any questions about significant figures in calculations? Any questions?
No.
No? Okay, good. Now let me deal with a more complex situation. And for that, I need to go back to this right here. And I'm going to skip, hold on. I'm going to skip to this. Okay, so what if you're doing a problem where it involves a combination of mathematical operations? Let me move this down here. Okay, so for example, we're doing this, right? Now, of course, we have in the numerator part of this setup here, we have a subtraction taking place. And then the result of that will be divided by what's down here as the denominator, all right? Now, based on what we have just looked at, we know that the rules for subtraction will be different from the rules for division. So the question now becomes, how do we deal with, you know, a 2-step process like this where the rules are different for each step when it comes to rounding off? And the answer is very simple. What you do is, for the first part here at the top where you're doing the subtraction, you round off according to the lowest number of decimal places. Now, let me just say this. If you were to do this in one go on your calculator, this is the answer you're going to get. You're going to get this on your display, all right? But you have to round this off appropriately. So the way you round this off appropriately is that you do the numerator first, the 1.039 minus the 1.020, and you're going to end up with this. And of course, you have to round that off appropriately. You have 3 decimal places here, 3 decimal places here, which means that the answer must be rounded off to 3 decimal places, which is what we have here. It turns out that this is also expressed to 2 significant figures, all right? So when you do the second part where you divide this by the 1.039, as I said before, you're going to get this on your calculator display, but because you have 2 significant figures here above and you have 4 significant figures below here, that means that you have to round off your answer to 2 significant figures, which means that the final answer, move this up here, which means that your final answer is going to be 0.018. So we drop these digits here and we end up with the final answer being 0.018. So that's basically what you do in a situation like this, where you have a multi-step process involving different mathematical operations which have different rules for rounding off. You do one part of it, then you round off accordingly, and then you do the next part and you round off accordingly, and you continue until you get your final correct answer. Okay, so that's basically what you do in that kind of situations. Okay, so let me get out of this and go back to this here. And let me, okay. So let's talk about problem solving. And basically the type of problem solving that we'll be looking at here is conversion, converting from one unit to the next. And in different textbooks, they call it different names, the method that is used. Some textbooks, they call it the conversion factor method. Other textbooks, they call it the unit conversion method. Same thing as far as I'm concerned. And this is used, as I said before, to convert from one unit to another. In order for us to do these conversions, we have to look at, and we have to know the relationship, the mathematical relationship between the two units involved. So for example, we need to recognize where we're converting from inch to centimeters. We need to identify the relationship between those two units, and that is given here. 1 inch is equal to 2.54 centimeters, all right? Okay, so these are just some other equivalences that are given. And this is, you know, a very concise, short table giving you some relationships, for example, between the kilogram and pound unit, between the gram and pound unit, between meter and inches, and so on and so forth. A more comprehensive list is given in the table I alluded to earlier. Let me show that to you here. So this is the table here. Let me put this down here. So if I were to scroll back up here and turn this around, whoops. Oh, no, I'm sorry. Okay. Okay, so this is a more comprehensive list of the different relationships. We have the relationships for length, mass, temperature, energy, pressure, volume, right? So just to highlight a couple of examples, 1 mile is equal to 5,280 feet, which is also equal to 1.6093 kilometers. 1 pound is equal to 453.59 grams, and so on and so forth. So these are the different relationships that you'll be using to do these conversions, all right? Okay, so let's talk about how do we calculate, or how do we carry out these conversions? And again, this is something that you should have met before. Okay, what did I do wrong? Let me go back here. Okay, so you could be asked, for example, how many centimeters are in 26 inches, all right? So let me bring this back up here. How many centimeters are in 26 inches, all right? So the way we set this up is that we start off with what we're given. We're given 26 inches. And then we multiply that by a conversion factor, which represents the relationship between the inch unit and the centimeter unit. And we have to make sure it's arranged correctly like this, where we have the inch unit down here and the centimeter unit up top. And that is important because we want to make sure that the inch unit will cancel out here and here, and you're left with the centimeter units remaining in your final answer, all right? So the next thing we need to do is put the numbers reflecting the relationship between the inch unit and centimeters unit. And we know already, we saw this before, that 2.54 centimeters is equal to 1 inch, all right? So we punch the numbers in the calculator, press the equal sign, and we get our answer, which we have to round off to 2 sig figs. Why? Because this is an exact relationship, right? So therefore, these numbers are exact numbers. So therefore, this has an infinite number of significant figures, while the number of significant figures here would be 2 significant figures, which means that your final answer must be rounded off to 2 significant figures. And therefore, the answer turns out to be equal to 66 centimeters. So that's basically how you would do that, all right? Admittedly, this is a relatively simple example. You can have a more complex example, such as this one right here. Now, in this case, we are converting from the foot unit to the millimeter unit. And as you can see here, because there's no obvious relationship between the foot unit and the millimeter unit, we have to go through a series of, in this case, 3 conversion factors, right? So the first conversion factor is the relationship between the inch unit and the foot unit. So this is how we set it up: 1 foot below as the denominator, 12 inches as the numerator, so that the foot unit will cancel out here and here. So up to this point, you'll be left with the inches unit. The next conversion factor is the relationship between the meter unit and the inch unit. We set this up such that the inch unit is down here and the meter unit is up top. The inch unit will cancel out here and here. And then the final conversion factor is shown here, the relationship between the millimeter and meter unit, where the meter unit is below and the millimeter unit is above. The meter unit will cancel out here and here. And then you do your number crunching and your answer turns out to be 381. again, you have to round this off to 3 sig figs because, well, let me explain something here. So the relationship between the inch unit and foot unit is by definition, and therefore this would be an exact relationship, all right? However, the relationship between the meter and the inch unit is not by definition, and therefore you have to take into account that you have 4 significant figures here. We assume that this here would be an exact number, the 1 meter here, but this here would be 4 significant figures, all right? This is an exact relationship, so these numbers are have an infinite number of significant figures. So basically, to decide how we round this off, we look at this here. We have 3 significant figures. This is exact. This is 4 significant figures. That's exact, which means that the lowest number of significant figures indicated here is 3. So that means we have to round off this answer here to 3 significant figures. So therefore, the answer would be 381 millimeters. All right, so that's basically how that is done. All right. Any question about this particular example? Any question? Any question?
No.
Okay. So some other quantities of measurement. Density. Again, this is something you should have met before. Density is a ratio of mass per unit volume of a substance. And in fact, the unit of density would be a combination of units of mass and volume. Now, the most common, oh, by the way, this is the formula for calculating density. Again, this is something you should know. Density is equal to mass divided by volume. The common units for density would be either grams per cm cube or grams per mil or grams per liter. Now, you should recognize that grams per cm cube and grams per mil are both basically the same. And that's because the centimeter cube unit is the same as a milliliter unit. And we typically use these two when it comes to expressing the densities of solids and liquids, all right? Now, the grams per liter unit is used when it comes to expressing the density units of gases. And the reason why is because gases are much less dense than solids and liquids. In other words, for the same mass, the volume of gases would be larger compared to the volume of solids and liquids. And therefore, it's more convenient to express the densities of gases using grams per liter as opposed to grams per mil. Now, some common substances are shown in this table and their densities. And as you can see here, solids and liquids are expressed in grams per mil or grams per cm cube, same thing, while gases such as air, argon, chlorine, etc., their densities are expressed in grams per liter. And what you're going to learn later on in chapter 5 is that the volumes of gases are subject to drastic changes when the temperature of a gas changes, all right? Which means that the density will change drastically as well. The same is not true for solids and liquids, all right? Because solids and liquids do not expand as much, for example, when the temperature increases, and therefore their densities don't change as much. And that's the reason why densities can be used as a physical property, which is one of the characteristics of solids and liquids. The same is not true for gases because their densities can change widely when the temperature changes. Okay, now another thing I want to mention here with respect to density is that one can express the density as a ratio, all right? So for example, in the case of copper, where the density is 8.94 grams per cm cube, you can express the density as 8.94 grams over 1 cm cube, or the reverse. You can have 1 cm cube above and 8.94 grams below. And which one you use is dependent on the type of calculation that you're trying to carry out. Okay, so that basically represents the end of chapter 1. Let me see here. Let me go to, I keep forgetting to give you a tour of the Canvas shell. So let me do that shortly. Let me look at the assignments for chapter 1. Okay, so based on what we have done so far, you should be able to do the assignments for chapter 1. So what I'm going to do is I'm going to publish firstly that folder, and then I'm going to get into the folder and publish. Okay, they're already published. And let me turn off the publish folders for chapters, for the other chapters. Okay, so basically chapter 1 assignments are available. Make sure that you download it, as I said before, complete it, and upload it as a PDF document. Let me make some changes here as well. So what I'm going to do is, well, I'm going to edit this so that this will be due on okay. So I'm going to let this be due on the 21st. All right. Let me, okay. Okay. Okay, so assignments 1 through 3 will be due on the 21st, all right? I'm going to set this due date for the others later on. Okay, all right, now, before I forget, let me take you through the Canvas shell for this course. So announcements will be located here. Make sure that you check it out so that you can be up to date on any changes that I would have made or anything I want to announce. The assignments, well, I'm not sure what this looks like on your end, but this is where I would publish the portal for the assignments and the due dates. The grades will be located under this link. Again, yours will look different. And let me see here. Now, as I said before, most of what you're going to need for this course will be located under files, all right? So I've just published the assignments, the textbook I talked about already. The PowerPoints from which I'm teaching from will be located in this folder right here. So you can refer to these, at your own, when you're studying, whatever. And the syllabus, of course, is located here, and the tables are located here. So that's basically where most of the things that you're going to need will be located. Now, I made reference to the fact that I'll be posting the video of each lecture in the module section, which will be located here, all right? So you click on the modules, and then you can click on the links provided. Now, these are links for previous videos I have created, but I have not published these. And I think this is actually for, let me check something here. Yeah, this is for introductory chemistry. So, I don't know if you want to watch these videos, but what I'm going to do is post the videos for this lecture. For example, the one that we're doing now, this will be made available under the modules link. So if you need to remind yourself of something, or if you need to rewatch these videos, or if you miss a class and you need to catch up, then you can catch up on the class, the MIST class, by watching the videos located in the module section. All right. And I think that's basically it. There's nothing else that you're going to need. Well, the Zoom link, of course, will be located on the Zoom as shown here. So, and I think that's it. I don't think there's anything else I need to show you. All right. So I just thought it was important that you know where to look for different things. All right. Any questions about Canvas? Any questions?
No.
Okay, so let me move on now to, didn't plan to do it, but since we are making good progress, let's move on to chapter 2. And again, chapter 2 is a bit of a review of things that you'd have done in your previous chemistry course. Chapter 2 is covering the topics of atoms, molecules, and ions, and other related topics. Okay, so we're going to look at a couple of laws of chemical composition. And the first one is the conservation of mass law. And if you look in different textbooks, you'll see that this is worded in different ways. So the way you see it's worded here is that the total mass remains constant during a chemical reaction. So that's one way of expressing the conservation of mass law. In other textbooks, you see something like in a chemical reaction, matter is not created nor destroyed. So that's another way of expressing the conservation of mass law. And an example of this law is demonstrated in the reaction where mercuric oxide is decomposed to form mercury and oxygen, right? So basically, if you start off with a certain mass of the original compound, mercury 2 oxide, and then you heat it to decompose it to form mercury and oxygen. And if you could isolate these two products, what you'll find is that the mass of the mercury plus the oxygen that is produced will be equal to the mass of the mercury 2 oxide from which it is formed. So that's basically what the law of conservation of mass is all about. Another law that we're going to talk about is what is known as the law of definite proportions. And what this law says is that all samples of a compound have the same composition. That is, all samples have the same proportion by mass of the elements that are present in the compound, all right? So for example, in the case of water, right? Water always contain 89% oxygen and 11% hydrogen. And that is true for every sample of water. It doesn't matter if the water is sourced from your tap, or if it comes from outer space, or if it comes from a river. If it is water, then the composition is always going to be 89% oxygen and 11% hydrogen. And that is true for all compounds. When you break them down into their constituent elements, the composition by mass will be the same for that compound, regardless of where that compound comes from. All right. Okay, so the next law we're going to talk about is the law of multiple proportions. And what this law says, and it's a bit wordy, I must admit, but it says here that when two or more different compounds of the same two elements are compared, the masses of one element that combine with a fixed mass of the second element are in the ratio of small whole numbers, all right? So just to illustrate what we're talking about here, there are two compounds that are made up of carbon and oxygen. One is called carbon monoxide, and the other one is called carbon dioxide. Now, if you're going to make these compounds from their elements, and let's say that you keep the carbon mass fixed in both cases, what you'll find is that the mass of oxygen that combines in each case of 3 grams of carbon will be varied by a factor of 2. So in the case of carbon monoxide, 3 grams of carbon will require 4 grams of oxygen, but in the case of carbon dioxide, 3 grams of carbon will require 8 grams of oxygen. So if you look at the ratio of oxygen to carbon, you see that it breaks down to 2 to 1, all right? And that is true for any 2 or more compounds which are made up of the same elements, but the composition will be different. What you'll find is that if you keep the mass of one of the elements fixed and you compare the masses of the other elements, the ratio of the masses of the other elements would be a whole number ratio. In this case, it's 2 to 1. In other cases, it may be 3 to 1, 3 to 4, whatever, all right? So that's basically what the law of multiple proportions is all about. Okay, let me continue to discuss now the atomic theory of matter. And this is a theory that was put forward by an Englishman by the name of Dalton, John Dalton. And based on what was known back then, he came up with this theory concerning matter. And we're just going to go through this, you know, all the different principal assumptions of this theory. Now, the first assumption is that all matter is composed of extremely small, indivisible particles called atoms. Now, let me just stick a pin here and state that we now know that this is not true, right? We now know that atoms are actually divisible and they can be broken down into smaller fragments. In fact, if you break down atoms into their most fundamental fragments, you'll find that atoms are made up of particles known as protons, electrons, and neutrons, all right? So this is one example of a theory that has been put forward. And then later on, scientists have examined the theory, tested it, performed experiments, and found out that one particular assumption turns out not to be correct, all right? Okay, let's look at the other principal assumptions. All atoms of a given element are alike in mass and other properties, but atoms of one element differ from the atoms of every other element, all right? Which is still believed to be true to this day based on what we know of atoms. Compounds are formed when atoms of different elements unite in fixed proportions. And a chemical reaction involves rearrangement of atoms, but no atoms are created, destroyed, or broken apart in a chemical reaction. And this particular assumption here is, of course, supported by the law that we talked about before, the conservation of mass law, right? Remember, we said that in that law, that matter is not created nor destroyed in a chemical reaction. And the reason why that is true is suggested by this particular statement in the atomic theory of matter. And that is that when you have a chemical reaction, there is no destruction or creation of atoms, but basically a rearrangement of atoms where bonds are broken and formed to form new products. Okay, so just to illustrate this theory, let's look at the reaction between hydrogen and fluorine to form hydrogen fluoride. Now, I'm sorry. Let me see here. Again, I'm going to try to do some writing here. Okay, so the equation we're talking about here is hydrogen plus fluorine to give 2H that's the equation for the reaction, right? So basically, and again, this is something you should know from your previous chemistry course. Okay, so basically, what this equation is saying is that one molecule of hydrogen will react with one molecule of fluorine to form 2 molecules of HF. Now, in this particular demonstration here, or illustration, we have 2 hydrogen molecules and we have 3 fluorine molecules, all right? So based on the 1-to-1 ratio between the hydrogen and fluorine here and the hydrogen fluoride, we know that these 2 hydrogen molecules, we know that these 2 hydrogen molecules will react with these 2 fluorine molecules to form 4 hydrogen fluoride molecules, and 1 fluorine molecule will remain unreacted, all right? In this case, you see no atoms created nor destroyed in this reaction, all right? And therefore, that's basically what's being demonstrated as that part of the atomic theory that we're highlighting here, right? The same number of fluorine atoms that we have on this side is equal to the same number of fluorine atoms we have on the left side, and the same is true for the hydrogen atoms. They're the same on both sides, all right? Okay. As I said before, we now know that there are subatomic particles present, in the atom of in the atom of an element. So we know that the protons and neutrons are located in the nucleus of the atom, whereas the electrons are dispersed around the nucleus. And this table here gives you a short summary of the different subatomic particles, where they're located, etc. So the proton symbol is given here. The approximate relative mass is 1 and the charge is +1. And as we said before, it's located inside the nucleus. The neutron has the same relative approximate mass, but the difference is that it has no charge, right? The neutron has 0 charge while the protons have a +1 charge. And then, the neutron is also located inside the nucleus. And then finally, the electron has a much lighter mass, has a charge of -1, and it's located outside the nucleus, all right? So that's a summary of the different particles located in the nucleus. Another term that you should be familiar with is this term isotopes. Isotopes are basically atoms that have the same number of protons, but different number of neutrons, all right? And let me just say also that you should be familiar with the term mass number, right? The mass number is the number of protons and neutrons in an atom. And the atomic number, which is another term you should be familiar with, gives the number of protons in the nucleus of an atom of an element, all right? So the atomic number is the number of protons, and typically or conventionally, the atomic number is represented by the uppercase Z, right? If you look in most textbooks, you'll see that representation for the atomic number. Okay, there are a couple of ways of expressing isotopes based on the mass number and atomic number. So for example, well, before we get into that, let me just highlight the example of the isotopes of hydrogen. There are 3 isotopes of hydrogen. You have hydrogen 1, which is simply known as normal hydrogen. And then you have hydrogen 2, which is known as deuterium. And then you have hydrogen 3, which is known as tritium, right? And as you can see, the difference between them would be the number of neutrons, right? They all have the same number of protons because they're all the same element. But in the case of ordinary hydrogen, the number of neutrons is 0. In the case of deuterium, the number of neutrons is 1. And in the case of tritium, the number of neutrons would be 2, all right? In all cases, the atomic number would still be the same, which is 1, all right? And that's the simplest example of isotopes. And of course, you have more examples of isotopes. Now I see somebody raise their hand, so.
Yeah, I have a quick question. So
Yes,
I
ma'am.
tried to go on Canvas to look at, can you still hear me?
Yes, I can hear you, yeah.
Okay. So I tried to go on Canvas to like see the assignments. So then when I click on assignment, like for example, I clicked on assignment 1 and it doesn't show like no paper or no file to like download or anything like that. It's only a spot to submit the assignment.
Oh, okay, all right. So the actual assignment would be located in the file section. So what you do, let me show you how to do that. You go,
I see it, because it says PowerPoint chapter 1.
Right, exactly. Files, and then you go to you scroll down actually. And then assignments, I'm sorry, right here. So you click on that, and then you're going to click on chapter 1, right? And you have assignments 1, 2, and 3. These are all PDF documents. So you need to print them.
So you said go to files, because I'm trying to do it while you're on here. So if I go to files,
right.
Hold on. So I went to
Go
files.
To files.
And
then go to assignments.
It doesn't have on ours. It doesn't. Oh, okay. Now it uploaded. Okay. So chapter 1, 3 items. All right. I see it now. Okay.
Yeah. And then you just print them off and complete them.
Okay.
All right.
Alrighty.
Okay. All right. So let's continue. Hold on. Okay. What the hell? What did I do? Oh, okay, right. All right, so as I was saying, isotopes. So one way of representing isotopes is writing it this way. Carbon 14, for example, right? So the element name and then the mass number, right? That's enough for you to determine the number of neutrons and protons and so on, because carbon is the only element that has atomic number 6. So we know that 6 is the number of protons, and therefore the number of neutrons will be the difference between 14 and 6, and that gives you 8 neutrons in the case of carbon, all right? And even for something more complicated, like chlorine, it's the same principle. So in this particular isotope of chlorine, the mass number is 35, the atomic number is 17, so therefore that means that we can determine the number of neutrons, which in this case would be 18. And then even one that's more complicated, like uranium-234, the atomic number for uranium is 92, so therefore to get the number of neutrons, we subtract the 92 from the 234, and that gives you the number of neutrons. So that's how you can determine the number of neutrons, the number of protons and electrons in an isotope, if you're given this way of representing the particular isotope. So in each of these cases, the number of neutrons will be equal to the difference between the mass number and the number of protons, or the atomic number. Okay, I got it. Now this is where I really wish I had brought my writing tablet. Okay, I wanted to work through this example, but I cannot because I don't have my tablet with me. So what I'm going to do is skip over this example and come back to it next class. Unfortunately, that's what I have to do, all right? Okay, now let's talk about this term atomic mass. The atomic mass is, for an element, is the weighted average atomic masses of the naturally occurring isotopes of that element. And this definition is actually what's related to the example that is on the previous slide, which I'm going to make sure and do next class, right? Now, the atomic mass can be expressed conveniently in terms of what is called the atomic mass unit, right? Which is defined as exactly 1/12 the mass of a carbon-12 atom. And it turns out that there's a relationship between the atomic mass unit and the mass in grams, which is given right here. All right. So I'm going to show you, as I said before, how to calculate the weighted average atomic mass of an element. But suffice to say, what I'll say here is that the weighted average atomic mass takes into account not only the mass of the different isotopes, but what we call their relative abundance. Because what you'll find is that where isotopes exist in nature, they exist in relative fixed proportions. Let me see here. Okay, and that's all I'm going to say about that. You're going to see this, how this works out when we do that particular example that I'm going to do on Wednesday. Another thing I want to mention here, and this is a very common error that students tend to make at this level. There is a difference between the atomic mass and the mass number, right? And students very often confuse the two. So I gave the definition of the atomic mass here, right? It's actually a measured value. It's the weighted average of the masses of the naturally occurring isotopes for that element. So that's the atomic mass. The mass number is simply the sum of the number of protons and neutrons in an atom of an element, all right? So those are two different things, right? Now, in most legitimate periodic tables, what you'll find is that for each element, there are two numbers that are given. In fact, let me show you based on the periodic table that I have provided for you. Okay, so let me scroll this down here. Let me scroll up here. Okay, so let's take this periodic table right here, right? If you look at each element, each box, right, you'll notice that there are two numbers given for each element. So let's focus on beryllium, for example. So in the case of beryllium, you have a smaller number and then you have this larger number. The smaller number here would be the atomic number, right? So basically we know that beryllium has 4 protons in its nucleus. The larger number here, the 9.01, is the relative atomic mass of beryllium. That number is the weighted average atomic masses of all the isotopes of beryllium, all right? That 9.01 is not the mass number, right? The mass number is the number of protons and neutrons present in an atom, right? The 9.01 that you see there for beryllium is not the mass number, it's the atomic mass. And students always confuse those two. So it's very important that you understand the difference and distinction between the mass number of an isotope and the atomic mass of an element. Okay, let's see here. Let me go back to, oh, you know what? Another break. So it's 11:51. So we're going to get back together at 12 and finish up on our first class for today. All right. I'll be right back. Okay, so we're going to resume again. Okay, what shall we talk about next? Let's see here. Okay, so a few comments about the periodic table. We're going to get into the periodic table in more detail later on, but this is just some introductory comments about the periodic table. The periodic table, the first periodic table that was ever put together was done so by the guy that you see here pictured to the right. His name was Dmitry Mendeleev. And I think, if I remember correctly, one account that I read about how he came up with this whole idea of the periodic table was that he noticed while writing a textbook that, and this is based on the elements that were known back then. He noticed that if you arranged the elements that were known back then according to their atomic masses, after so many elements, you notice that certain properties start repeating themselves, all right? Now, back then, there was no notion of protons and neutrons and so on. So therefore, the concept of atomic number wasn't known back then. So the only thing that they needed or that they knew that would identify the different elements would be the atomic mass. And that's what he had to work with. And that's what he used to determine or to put together his version of the periodic table. So he developed the table, put elements that behave a certain way in columns known as groups. And what he noticed when he did that was that there are certain gaps in the periodic table which represents elements that were not yet discovered. When those elements were discovered, it was found that the properties that were discovered by those elements were predicted by Mendeleev to a very uncanny degree. All right, so Mendeleev deserves a lot of credit for doing what he did. Of course, as the years go by, other elements were discovered, and the periodic table that he started off with underwent some changes, and therefore we end up now with the current version of the periodic table. Okay, so this is the periodic table here that we're all familiar with. And as you can see, the elements are arranged in groups and periods. The periods are, of course, the rows, and simple numbering system is used, row 1, 2, 3, all the way to row 7. And then we have the groups, which in this case is 1A, 2A, and so on and so forth. The most modern periodic table now simply just number the groups from 1 through 16, through 18, going from left to right of the table, all right? Now, when it comes to broad categories, elements are divided into two main classes, all right? You have what are known as the metals, which are to the left of the periodic table, and you have the non-metals, which are to the right. Excuse me. You have a third category of metals or elements known as metalloids. And the metalloids are located on one or the other side of this line here. You see this thick line right here, right? That basically serves as a line of demarcation between metals and non-metals. So the non-metals would be on the left, on the right, and the metals would be on the left. But you have elements such as silicon, arsenic, antimony, which are considered to be metalloids. And basically what that means is that these are elements which displays characteristics of both metals and non-metals, all right? Okay, let's talk about formulas. Formulas is basically a shorthand way of representing the composition of a particular substance. And so for example, in this particular formula here, what this is telling you is that for every 2 boron that is present, there are 3 oxygen present, atoms present in this compound, all right? So that's what these subscripts represent, the number of atoms that are present in a particular unit of this particular compound. Okay, and when it comes to molecular compounds, which are made up of non-metallic elements, there are different representations that you can show. These are different models. We have the ball and stick model here. So each ball represents a particular atom. And then you have the space filling model, which we met before. If you remember, we looked at the water molecule. And these are other space filling molecules. This is for chlorine, and this is for sulfur, which is a polyatomic atom or polyatomic molecule. The model that you use to represent a particular compound is dependent on what you're trying to express. So for example, in this case here, if you want to show how the atoms are connected to each other in a 3-dimensional way, the ball and stick model would be the way to go. But if you want to show the space filling properties of the different atoms in the compound, then you'd go with the space filling model. The space filling model is usually used by people engaged in biological chemistry, biochemistry, medicinal chemistry, pharmaceutical chemistry, and so on. Okay, empirical and molecular formulas. Again, this is something you should have known from before. So the empirical formula for a substance is the simplest whole number ratio of the atoms of the elements in a compound. That's what the empirical formula gives you. While the molecular formula gives you the actual number of atoms of each element present per molecule. So for example, in the case of glucose, the molecular formula is C6H12O6, because what that tells you is that for every molecule of glucose, you have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. The empirical formula for glucose would be CH2O, because what that tells you is that for any sample of glucose, the ratio of carbon to hydrogen to oxygen is 1 to 2 to 1, all right? So it's very important that you understand the difference between the two and the relationship between the two. In some cases, the molecular formula and the empirical formula would be the same. So a good example of that would be water, H2O, right? H2O is both the molecular formula and the empirical formula for water. In other cases, such as in the case of glucose, in order for you to get from the empirical formula to the molecular formula, you have to multiply the empirical formula by some integer in order to get to the molecular formula. So for example, in the case of glucose, you'd have to multiply the empirical formula by 6 to get to the molecular formula. All right, and later on, we're going to see how we can achieve that based on some calculations that you'd have to do. Okay, I'm going to say that the last thing we're going to talk about here is, let me check something here. Okay, the last thing we're going to talk about here is structural formulas. And again, this is a way of representing how atoms are connected to each other in a molecule. And for those of you who plan to do organic chemistry, you're going to see a lot of this sort of representation, all right? And basically, each line represents a shared pair of electrons, which constitutes a bond. So for example, in the case of methane, this carbon is simultaneously bonded by a pair of electrons each to a hydrogen atom, to 4 hydrogen atoms, all right? Acetic acid here is a bit more complex, but basically it's the same idea in terms of how the atoms are connected to each other. Okay, I'm going to stop here for today. Unless there are any questions you have to ask. Any questions?
No.
Okay. All right. So that's basically it for today. So we're going to meet up again on Wednesday at 9. All right. So until then, take care. Enjoy the rest of your day.
Okay. Thank you.
All right. All right. No problem. Take care. Let me see this one. Okay.